Welcome to ExceLworks video tutorials. The title of this presentation is how to differentiate a graph of XY points in Excel and Google Sheets with the function DERIVXY. Typically, you have collected some empirical data points, for example, displacement versus time, and you've graphed them. Now you want to differentiate this graph to obtain your velocity or even your acceleration, which is the second derivative. In this presentation, we will show you how you can do that quite easily with the DERIVXY function in both Microsoft Excel and Google Sheets. Let's begin by introducing the function DERIVXY. DERIVXY takes three required parameters. The first parameter is a vector of x points. The second parameter is the corresponding y values for your x coordinates. The third parameter is either a single or a vector of points at which you want to compute the derivatives. And it takes additional three optional parameters. The fourth one is the order of the derivative you want to compute. The default is the first derivative. You can pass 2 or 3. The fifth argument is a set of control keys and values for the algorithm. We'll talk about this later. The sixth argument is a set of weights that will give you the ability to discriminate against your data. DERIVXY algorithm is based on cubic splines. Unfortunately, DERIVXY is not a standard function in Excel or Google Sheets. To enable DERIVXY in Excel or Google Sheets, you'll have to install the ExceLab calculus functions add-in. If you are running Excel on a Windows PC, just download and install ExceLab 7 from excel-works.com. If you are running Excel on an Apple Mac, install ExceLab from the Microsoft App Source. From your Excel ribbon, click Insert, Get Add-ins, search for Calculus, and then add the add-in. If you are working with Google Sheets, search on the Google Marketplace for the function the Calculus function add-on and install it. We will demonstrate the use of DERIVXY using the function I have shown here. Typically, you don't have a function, you just have measured data. But in this tutorial, we want to see how good DERIVXY calculates the derivative by comparing it to the known derivative. Next, we will also show you how you can improve your results near the boundary points. So let's get started by working in Excel. We'll be doing the demonstration in Excel, but the procedure is virtually identical in Google Sheets. I'm going to start from 0 at an increment of 0.2 all the way to 3. Next, let me generate the y points using the formula here for the function. And autofill to complete the values. Next, I'm going to use DERIVXY to compute the derivatives at the x values. The first argument is the vector of x points. The second argument is the vector of y points. And the third argument is, in this case, a vector of the x points as well. I want to generate the derivatives at all the x points. I happen to work with ExceLab 365, which has a nice spell feature. So as you can see here, I evaluated the DERIVX formula as a standard formula by hitting enter. Although I am generating a vector of results, it automatically spells into neighboring cells. To see how well we did with the accuracy, let's compare these numbers to the exact derivatives at these points using the known derivative formula. I'm going to generate the exact derivatives next. Let me name this column first as DERIVXY, and I'm going to generate my exact derivatives in this column here using the analytical formula. Bear with me as I type it in. and we'll use autofill to get the rest of the values. Now let's look at the difference between the two. So we're doing generally okay. This is the absolute difference here, except where we get too close to the boundary. Why don't we plot this and see how they look like? Choosing my X vector, my Y values from the DERIVXY, and my Y values from the analytical formula. Next, I'm going to insert an XY plot. As you can see here, we're matching pretty much everywhere except as we get near the boundary, and that's expected because splines require boundary conditions to give you exact fit near the boundary, and the boundary conditions was not supplied, so it uses a default boundary condition. Now we can actually improve that result in this case because we know what the boundary condition or what the slope at this point should look like because we have it from the analytical formula, so we can supply it as optional argument to DERIVXY. So why don't we do that? I'm going to define some optional arguments here using some control keys. My first key is I slope, and my value here from the analytical is 0. And the next key is end slope, and my value here from the analytical formula is -15. I'm going to supply the slope information to DERIVXY using the optional argument number 5. So I'm skipping over optional argument 4 because we're just calculating the first derivative, and here I'm going to reference this controls. As you can see now, our errors have improved significantly here, and if we look at the chart, they're almost identical. Generally, you do not know what the derivatives are at the endpoints, but if you have a good estimate of what they are, you can greatly improve the accuracy of the calculation. One more thing I would like to quickly demonstrate here is I can now easily calculate higher order derivatives simply by passing 2 for the second derivatives or 3 for the third derivative in argument number 4. One important point I would like to emphasize here is how you calculate multiple values at once using either array formula or spell. In the previous demonstration we showed how to use this new spell feature, but that will not work in the standard version on the Windows. That will only work on Google Sheets and Macs or with Office 365. So you have two options when you want to run DERIVXY as an array formula for calculating multiple derivatives at once. Either you could evaluate it using the autofill feature, and in this case you have to lock the first two parameters and only vary the derivative point, or you must run it as an array formula, which is a lot more efficient. And here you can either use the spell feature if you happen to use ExceLab 365 or Google Sheets, or you have to run it the standard way by highlighting the output array and clicking Ctrl-Shift-Enter at once. Let me demonstrate this in Excel. So I'm back in Excel. Let me move these out of the way. This is my original evaluation, and I'm using here the spell feature by simply hitting enter, and it automatically expands the neighboring cells. If I were using ExceLab 7 on a Windows platform, I can't do that. So the way you would do it is you must first highlight your output array, define your formula, and hit Ctrl-Shift-Enter. So let's first copy the formula here that we want to evaluate. Then let's highlight the output array, click in the formula bar, copy our formula, and then now I need to press Ctrl-Shift-Enter at once, and we calculated the formula as an array formula. If you notice here, Excel automatically places curly brackets around the formula to indicate that this value is an array formula. The other way you could do that is by the autofill. So let me get this formula one more time, and I am going to copy it here and just evaluate it at one value. Now before I can use autofill, I must lock my first two parameters using the $sign syntax. That will prevent Excel from changing these values during the autofill. In this case, it suffices to lock just the row number because we're not changing the columns here, but it doesn't matter. I'm locking both of them. So nothing has changed. Now I'm able to use the autofill to complete the rest of the values. Now a word of caution here. It's recommended that you use the array formula to calculate multiple values at once. It's a lot more efficient and it does not tax the server like the autofill does. Let's talk a little bit more about the advanced optional features for DERIVXY, which apply when you're working with real-life experimental data. Typically, when you generate empirical data, they are likely unsorted. They are likely to contain duplicate measurements where you have one value for X but multiple values measured at the same point. And they might be statistically biased, so some measurements are more accurate than others or more significant. And you might have specific requirements where this data is sampled from a periodic way, for example, or it might contain some white noise that you would like to filter out before you do the differentiation. For the first two items here, the good news is actually they are handled automatically for you. So DERIVXY will sort the data for you if they are unsorted, and it will average the duplicate measurements at any given point automatically. Now with the statistically biased data, you have some controls over this, and I'll show you this in the next slide. Weighing your biased data. In the table to the left, I am showing some data here where I know, for example, that the first and last 2 points are less accurate than the one in between. So I can use optional argument number 6 to weigh my data to emphasize or give more emphasis to some points over others. The weights have to be strictly positive. 1 is the most significant, and any values less than 1 represents the relative importance of a particular point with relative to the other points. Once I have that vector, I can supply it in argument number 6, and the algorithm will factor this information in when doing the spline fitting. Now, if your data has white noise that you would like to null it before you do the differentiation, you can use a smoothing factor in the optional argument number 5. And that's done with the key S factor. You would assign a value for this key. The default value is 0, which implies no smoothing. But if you assign any larger value, for example 100, it will compute the derivative based on a least square smoothing curve fit. Boundary conditions. Largest source of errors is actually happens at the boundary. So you can mitigate this in 2 ways. If you can estimate the slopes at the endpoints, the initial slope and the end slope, you can directly supply them in optional argument number 5, as we have demonstrated in Excel. The second thing is, if you know that your data is periodic, you can set the value of the periodic keyword to true, and that will automatically take care of the end boundary conditions for you. In this presentation, we described the DERIVXY function of the calculus functions family in ExceLab 7, and there are a dozen other functions for various calculus operations, including integration, differentiation, interpolation, solving equations and differential equations, optimization. If you are interested in any of these problems, visit excel-works.com and check out the examples. Thank you.